Hi Lokesh, do you have any question? Sorry, you just raised your hand. You have any question? Okay, okay. So it's 3:05 p.m. I think we can start. So let me just share my screen first. So hi everyone. I welcome you all to this live session 9 of the course Digital Electronic Circuits that is taught by Professor Gautam Saha from IIT Kharagpur. I am your course TA Musab Rafiq from IIT Kanpur. I am a PhD scholar in the Department of Electrical Engineering. Today we will be going to discuss problems related to week 9 lectures. So this is a live session and also recording will be made available on the YouTube. So let me just start. So today we are going to discuss week 9 lecture questions related to week 9 lectures. So in this live session we'll cover questions related to counters, synchronous, asynchronous, ripple counter, Johnson counter, ring counter. And let me just give the instructions. So as the number of participants are less in the live session, so you can use your mic to ask in any doubts, but if possible ask your doubts after a particular problem is solved. I'll give you the sufficient time to ask in your doubts, and new participants will be added only after I solve a particular problem. In between, while I'm solving a problem, I won't be able to admit them. So without further ado, I think we can start with the question number 1 of today's live session. So since the number of participants in live session is very less, so I'll be just going very slowly over these questions because I won't be able to get the feedback whether I'm going fast or slow. So I'll be going very slowly so you guys can understand better. So let me just start with the first question. So it states that a ripple counter with a positive edge triggered flip flop is given below. So we have a positive edge triggered flip flops which are in a cascade configuration to form the ripple counter. Here you can see a T flip flop, and here the clock is connected to this, and this output from flip flop 1 and 2. So we need to find out the next state if the present state of the counter was 110. So Q0 is equal to 1, Q1 is equal to 1, and Q2 is equal to 0 was the present state, and we need to find out the next state. What will be the next state of the counter? So as you can see, input to the T flip flops are 1. So with every rising, so since a positive edge trigger, so with every rising edge at the clock, they will toggle. So let's just write the present state first. So as given, present state is Q0 is equal to 1, Q1 is equal to 1, and Q2 is equal to 0, right? So since this is connected to Q0, Q0 complement is connected to the clock of this flip flop. Let's just name it as 0, and this as 1, and this one as 2. So since clock of Q1 is nothing but is Q0 complement, since with the transition of a clock as the positive edge trigger, Q0, which was 1, will transition from 1 to 0. So let me just write Q0 plus 1, which means the next state will be 0. That implies Q0 complement, Q0 complement, which was 0, will make a transition to 1. So that means there will be a positive edge here. So as a result, there will be a transition in this flip-flop also, that is labeled as 1. So this was also 1, that means Q1 was 1. It will also make transition to 0, and Q0 complement was 0, so it will make transition to 1, and this will again make transition, which was Q2, which was equal to 0, since there will also be a rising edge now. Q2 was 0, so Q2 plus 1 will be equal to 1. So the present state was 1 1 0. So after transition it will be, so let's just label, since we need to be careful with these labels. So Q0, Q1 and Q2 are the labels here. So Q0, Q1, Q2, the transition will be now 0 0 1. Q0, Q1 and Q2. So when we started from 1 1 0, so when we were at 1 1 0, our next state has now been to 0 0 1. So option B is the correct answer to this question. So any doubts here? So I guess there are no doubts. Let me just proceed to question number 2. So the question number 2 states that the number of used states of the counter shown in the following figure is, just a second, my camera is not working, let me just again put it there. Okay, it's working now. So question 2 asks us the number of used states of the counter shown in the below figure is. So we have I can see 3 flip-flops of JK flip-flops which are connected in some configuration, and we need to figure out how many used states are there. So as we can see, there are 3 flip-flops, so the possible states are 2 raised to power 3, 8 states, and among those 8 states we need to see how many are used states and how many are unused states, and we need to give our answer, which is the number of used states. So let's just first analyze the circuit. Let's just see what is happening. Let's just label it. So this is again 0 1 and this one is 2. So my input to J and K is 1. Okay, so my input to J and K is 1. So flip-flop 0, I can write J is equal to K is equal to 1, right? And for let's say mark a dash here, for brevity let's just mark a dash here. And now we need to look at the flip-flop 1. So we are at flip-flop 1. So my J, if I could follow it, it's coming from an AND gate. So it's an output of an AND gate. So let's just see what are the inputs to the AND gate. So this goes here. So it's Q2 complement. So J is equal to, okay, this was J0, this was A0, this was J1. So J1 is equal to Q2 complement ANDed with, so it's ANDed with Q0, yeah, I think, yeah, Q0, yeah. So it's ANDed with Q0, and K1 is what is K1? So this is this. K1 is, okay, K1 is Q0. K1 is Q0. So if you can see this one, K1 is Q0. Now flip-flop 2 will have inputs J2, that is again an output of an AND gate, so it's Q1, simply Q1. And what is else other input? Q0, again Q0. And K2 is so this is here, K2 is Q0, simply Q0. Let me just cross check them whether I've written it correctly. Yeah, they are right. So now what we'll do, we'll make a clock. So let me just use another slide here, or can I write it here? Let me just try to write it here. So I can construct a clock here. So this is clock. So they are not same. So since they are negative edge triggered, let me just mark the negative edges. So Q0, let's just assume they start from 0 0 0. Q0, since Q0 is connected to J equal to K equal to 1, it will always toggle. So what we'll do, we'll just mark it here. Q0 will always toggle as at the falling edges, because my J equal to K equal to 1. So this will be like this at all falling edges, it will toggle. Right. So this was 0, this is 1, this was 0, this is 1, this was 0, this is 1, again 0. Now Q1 will start from 0, and at the falling edge, what will be my J1? My J1 will be Q2 complement dot Q0. So it will be 1 and with 0, so it will be 0, and K will be again 0, so it will be memory. So my J equal to K equal to 0, so it will remain at 0. What will be my Q2? Q2 is equal to Q1 Q0, so it will be again 0. Q2 is equal to Q0, so it will be again 0, so it will remain as 0. So this is 0, this is 0, this is 0. Now what will be my Q1? So I need to find out J1 and Q1. J1 will be 1, J1 will be 1 and with 1, so J1 is equal to 1, and K1 will be 1, so it will toggle, so it will be 1, and my J2 will be K1 dot, so J2 will be 1, and J2 will be Q1 dot Q0, so Q1 is equal to 0 and Q0 is equal, so it will be 0, and Q2 is equal to 0, so it will remain at memory, so it will be 0 here. Now in this cycle, so my Q0 is equal to 0, and my that means J1 is equal to 0, and my K1 is again 0, so it will remain at J1 equal to 0, K1 equal to 0, so output will remain same, so that is 1. And here my J2 is equal to Q1 is equal to 1, and Q0 is equal to 0, so it will be 0, and Q2 is equal to Q0, so it will be 0, so output will be 0 for Q2. Now coming to this point, my Q1 is 1, my Q0 is 1, and my Q2 is 0, so Q2 complement will be 1, so J1 is equal to 1 and K1 is equal to 1, so it will toggle, so it will be 0 and it will go to 0, and Q2 will be Q1 is equal to 1 and Q0 is equal to 1, so it will be 1. Q2 is equal to 1, so it will toggle, so it will be 1. Similarly, we will have 0 0 here and 1 1 here, and again 0 here and again 0 here. So we started with 0 0 0 and we are again coming back to 0 0 0. So the number of states are 1 2 3 4 5 6 7. So this is again repetition, so there are only 6. So out of the 8 states we are using only 6 states. So in terms of Q2, Q1, Q0, 1 1 1 and 1 1 0 are unused, and all other are used, as you can see from here. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 and again 0 0 0. So total we have 6 states. So the number of used states shown in this counter is 6. So any doubts in this question? So now let me just discuss question number 3. So the question number 3 states that consider the circuit below. Let the propagation delay of NAND gate is 2 nanoseconds. So the propagation delay of NAND gate is 2 nanoseconds, and that of the counter is 0. So the approximation is counter delay is 0. If the applied clock frequency is 1 gigahertz, the module of the counter is. So let's just first assume that there was no delay for this NAND gate. So if there was no delay for this NAND gate, what would have been the modulus of this circuit shown here? So the counter will have started from 0 0 0. So Q2, Q1 and Q0. Then it will have gone to 0 0 1. Then it will have gone to 0 1 0. The moment it will hit 0 1 0, so it's 0 1 and 0. There will be a reset signal, and this thing will reset. So we will again start with 0 0 0. That means it would have been a 3-state mod 3 counter, but there is a delay in the NAND gate. So the delay is, let me just write it here. So the propagation delay of NAND gate is given as 2 nanoseconds. So the propagation of delay is 2 nanoseconds. That means once the inputs are here, to get the outputs it will take 2 nanoseconds. But the counter is not having any delay because the approximation is counter is having 0 delay. So for the output to reset, to get the output of the NAND gate and to reset this counter, it requires 2 nanoseconds, and in those 2 nanoseconds it will give 2 more states, which are 0 1 1 and 1 0 0. Why it will give 2 more states? Because the output frequency frequency of the counter is 1 gigahertz, and we have a propagation delay of 2 nanoseconds. So that means we have 2 nanoseconds, and that means we can have 2 more states, and as a result the counter will now this circuit will now count 3 plus 2, that is 5 states. So this thing, which was a 3-state counter because of when the NAND gate was ideal, now as there is a propagation delay in the NAND gate of this 2 nanoseconds, it will count 2 more states. So this counter will be a mod 5 counter. So any doubt in this question? So let me just again repeat this point, maybe some you might be confused. So this NAND gate, people might be wondering why this 0 1 0. So there are these bubbles which signify complement. So why I stop at 0 1 0? Because when I complement this, my input to the NAND gate will become 1, and this is not any complement, so it will be 1, and this 0 will again be 1, and my output will be 0, and this will reset the signal, and this will reset the counter. So as soon as my output is 0 1 0, my counter will be reset. But that is when the output is immediately coming as soon as the input is here, that is no delay. But once there is a delay, the counter, since it is operating at 1 GHz frequency and the delay here is 2 nanoseconds, it will count 2 more states in that 2 nanoseconds, and when these 2 nanoseconds are passed, it will reset. So the number of states are 3 plus 2, so there are 5 states, so it's a mod 5 counter. Option C is the right answer. Now moving forward to question number 4. What is the modulus value of a 5-bit ring counter? So when we talk of a ring counter, so we have these flip-flops. Let us mark it as 1 and D flip-flop 2, 3. In ring counter we have this Q and Q and Q and Q. The output of the last flip-flop is connected to the input of the first flip-flop, and this form as a ring counter, right? So this is a ring counter, and in ring counter the modulus of a ring counter is equal to the number of flip-flops. So the number of flip-flops here are, since it's a 5-bit counter, it's 5. That implies the modulus is mod 5. So a 5-bit ring counter has a modulus of 5. It's a pretty simple question. I assume there are no doubts in this. So now going forward to this question number 5, we need to find out what is the mod value of low counter. So we need to find out the modulus value of low counter. So since it may not be visible to everyone, so let me just highlight this. This is A0, this is A1, this is A2. Here it is a typo, this should be read as A3. So this is A3, this is A2. Here what we have this count enable, which will start the counter signal, and that's going to this AND gate, and then we have this AND gate, and finally we have this thing to connect to next stage. So we only need to worry about this thing, and we need to figure out what is the modulus value of this. So how will we do it? So let's just construct let me just put it right here. Let's just construct our first clock. Let's first write what are the value of J0. Let me just label this one. This is 0, this is 1, this is 2, and this one is 3. So my J0 equal to K0 is equal to count enable, that I will write CE in short, right? And my J1 is equal to K1, because they are both connected to the output of this NAND gate. And what is that output of NAND gate? AND gate equal to, this is count enable, and with output of this first flip-flop, that is A0, right? Then I have J2 equal to K2, this thing ANDed with this thing, so this is CE AND with A0 and with A1. Then for J3 equal to K3, I have CE A0 AND with A1 and AND with A2. So these are my inputs. Now let me just write clock here. So this is the first clock and this is the initial. So let me just write it initial. My initial states are A0, So let's first write the MSB first. A3, A2, A1, A0. They are 0, 0, 0, and I don't know about anything about J and K, so let me just write that this. Now when the first clock pulse comes, since they are positive edge trigger, that's why I've shown this label as positive edge trigger. When my first clock comes, my J equal to K equal to 1, so my A0 will toggle, so it will go to 1, as J0 is equal to K0 is equal to 1, and it will always remain as 1 from now. So it will be 1 for all conditions, so that means the output will toggle always, so it will be 0, 1, 0, 1, and so on. So let us not write these things first. Let's concentrate on the next clock cycle. So first clock cycle only. So J0 is equal to K0 is equal to 1. So J1 is equal to K1 is equal to count enable dot A0. A0 was 0 in previous cycle, so count enable dot 0, so it will be 0, so it will remain at 0, 0, and same for all other. Now my second clock pulse, as I told you, my J0 K0 is 1, so it will toggle, so we don't need to worry about that thing. That thing is sorted for now. My J1 will be equal to count enable, that is 1, and with A0 that was 1, so it will be 1. And my J2 will be equal to count enable and with A0 that is 1, but A1 was 1, 0 in previous cycle, so it will be 0, and same for A3. Now clock cycle here, A3. Let me just use this thing, maybe some people might get confused. Now I am at clock cycle 3, so my output will go to A0 will go to 1 because it's toggling. My J1 is equal to K1 C dot AE, so it will be 0, 0, and as it is 0, 0, so see what I am saying. J1 equal to K1 is equal to count enable dot A0. Count enable was 1 and A0 was 0, so it will be 0, 0. J1 equal to K1 equal to 0, 0. That means output will be equal to previous output, so it will remain as 1. My J2 equal to K2 is equal to 0, 0, so it will remain at 0, and same for this. So let me just write it here. Then we have another clock cycle here. Where is this? So here my A0 is 1 and C is 1, so my J1 and K1 are 1, so output will toggle to 0. So my C dot A0 is 1, and my A1 was also 1 in previous cycle, so output will now toggle, so it will be 1 and it will be 0. So then in next cycle this will be 0 and this will be 1 and this will be 0, so on up to, and now you might have the idea. So what will be the 15th? This was 1, 2, 3, 4. This was clock 1, 2, 3, 4. This was 5, and so on. Finally for the 15th one we will have 1, 1, 1, and 1. And when I am giving the 16th clock pulse, so my states will be 0, 0, 0, and 0, because all of them will toggle. So this is simply a mod 16 counter, because it's counting 16 states from 0, 0, 0 to 1, 1, 1, 1. So this is simply a mod 16 counter. So any doubts, please ask in. Let me just take a 2-minute break. In case you have any doubts, please type in. Okay, we can resume now. So this was question number 5. Now we can move forward to question number 6. So question number 6 states that for the circuit shown below, the clock frequency is f0, so f0, and the duty cycle is 25%. So the duty cycle means the time ratio of on time by total time. So that means out of the total time period, for 25% of that time, my clock is high. And so we need to find out for the signal at the output Q what will be the frequency and duty cycle. So this is the circuit. So this is a 2-bit binary counter connected to this flip-flop. We need to find out the what will be my clock frequency at this here. So we need to find out here and its duty cycle. So let's just draw the clock first. So I can draw it like this. Not equally spaced, but we can work with that. So since only LSB is connected to this J and K, so what are the states of 2-bit binary counter? So it's 0 0 0 1 1 0 and 1 1. So this is my MSB, this is my LSB. So LSB is going from 0 1 0 1. So at positive edges my LSB is changing from 0 1 0 1, and which is nothing but my J equal to K. So my J equal to K equal to LSB starting from 0 0 0 is 0, then it will remain at 1, it will go to 0, it will remain at 1, it will go to 0, and it will remain at 1 and go to 0. So this is 0 1 0 1 0. So let's just assume that our initial state of the flip-flop was equal to Q equal to 0. So here at the rising edge of the clock, my input is changing from J equal to 0 equal to J equal to K equal to 0 to J equal to K equal to 1. So that means the output will toggle. So if it was 0, it will go to 1. And my now at this rising edge, my input, which is J equal to K equal to 1, is changing from J equal to K equal to 1 to J equal to K equal to 0. That means the output will not be changed, it will remain at previous state. And here my output is changing, so let me just erase here. It's changing from J equal to K equal to 0 to J equal to K equal to 1. So it will change like here. So what was initially f0, my output frequency will be f0 by 4, and it will have a duty cycle of 50%. So you can see here it will have a duty cycle of 50%. For the 50% of time it will be on, and for the 50% of time it will be off. And in fact, even if this duty cycle of the clock was 50%, my output will still have been by f0 by 4 and with a duty cycle of 50%. So that thing would not have been changed. So my answer is frequency is f0 by 4 and duty cycle is 50%. That is option A. So why it's having a duty cycle of 50% here? Because 0 0 states 0 0 will not change the previous state, and only J equal to K equal to 1 will change the states. That's why the duty cycle is coming out to be 50%, and frequency is getting divided by 2. And frequency is also getting divided by 2 because of this thing. So it is f0 by 2 by 2, that is f0 by 4. But you can draw the waveform, then you can get the frequency to be equal to f0 by 4. So any doubts, please asking. Now let's move to question number 7. So the question number 7 asks us, consider the following figure. So we have these JK flip-flops here. Suppose you are asked to make a decoding circuit such that the output y equal to 1. So y equal to 1 when the counter is at state 0, 1, 6 and 7. So when the counter is at state 0, 1, 6 and 7, my output should be equal to 1, y equal to 1. So what I am looking for is y equal to 1. So the question is asking what will be the gate which we are going to require to get this thing. So so what the question is asking is, using a single gate, which of the following can be used to implement the given logic operation. So we need to figure out which logic gate should I put here. So my output y equal to 1 for whenever the counter is at state 0, 1, 6 and 7. So what we will do, we will just write the first the MSB C B A, and here we will write the state. So 0, it will be 0, 0, 0, then 1, 1, 0, 1 and 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, then 1, 1, 1, 1. This is state. This is 0, then 1, 2, 3, 4, 5, 6 and 7. So output should be 1 at 0, 1, 6 and 7. But if you carefully examine this is a logic gate, and then we have this thing, the bubble here. That means we have a logic gate whose complement is y. So we need to write our logic gate should implement the functionality y not equal y not y complement should be equal to 1. So we need to write 1 for those things where the y complement is 1, then that complement will be equal to 0 and 0 will be equal to 1. So what I mean to say, so if my output here out of the logic gate is 0, it will go to a NOT gate and it will give me 1. So if my desired output was 0, 1, 6, 7, but for the logic gate output it will be 2, 4, it will be 2, 4, 2, 3, 4, 5. 2, 3, 4, 5 will be equal to 1, and other 0, 1, 6, 7 will be equal to 0. So this is the output of logic gate. This is y output of logic gate y not. So this will be 0, this will be 0, this will be 1, 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 this will be 0 and this will be 0. So we can use a K-map here to find the logical expression to implement this. So here we write C, here we write B and A. So this is 0, this is 0, then it is 1, 1, then it is 1, 1, then it is 0, 0. So we'll have this thing and we'll have this thing. So my y complement will be equal to, this is C complement, and what is changing is 0, 0, 0, 1. This is C 1, 1, 1, 0. This is C complement, and this is C complement A. This is what is this? This is okay. This is C complement B plus this is C, and what is changing B. So what is y not complement? So y not complement is B complement C plus B C complement. So this is simply an XOR gate. So an XOR gate will be inserted here that will have this functionality, because this finally we have this complement here. So that's why we wrote zeros for 0, 1, 6, 7 and 1 for all other cases. So the required gate will be an XOR gate. So when we put XOR gate here, it will do the required functionality. If there are no doubts, we can move forward to question number, this was 7, now question number 8. So the question number 8 asks us, a certain JK flip-flop has a propagation delay of 40 nanoseconds. The largest modulus of ripple counter that can be constructed from such flip-flop and still operate up to 8 MHz is. So we are given this propagation delay of a JK flip-flop is 40 nanoseconds, and we know that for a mod and ripple counter, the overall propagation delay is NTPD, and the frequency is simply f is equal to 1 by NTPD. So the condition that has been imposed on us is what will be the value of the largest modulus that we can construct out of this thing, and that will be operating at 8 megahertz. So f is equal to 8 megahertz. So that implies n is equal to 1 by f into the individual propagation delay of a JK flip-flop. So then it will be 1 by 8 megahertz, that is 8 into 10 to the power 6 multiplied by 40 into 10 to the power minus 9. So it will be 1 by 32 into 10 to the power, this was 7, 10 to the power minus 2. So this is 100 by 32, that is approximately equal to 3.125. So we can write it approximately, that is equal to 3.15, we can write it approximately equal to 3. So these are the number of flip-flops that will be present in there, and the number of states then will be equal to 2 raised to power n, that is equal to 2 raised to power 3, that is equal to 8. So it will be a mod 8 counter. So the largest counter that is possible out of this thing is a mod 8 counter. So option D is correct answer. So one thing I would like to point out here is option 3 was also given, option equal to 3 was also given here. So sometimes in a hurry we will just find out that the number of flip-flops required was 3, so we'll mark it here. So but we need to find out the modulus of this triple counter, so that's why we wrote the number of states that it will count, that's 2 to the power number of flip-flops, that is 3, so that's 8. So these things should be kept in mind while doing these questions. So any doubts? So let's just take a 2 minutes break and we can resume after 2 minutes. So now let's just discuss question number 9 of today's live session. So question number 9 states that the initial state of the counter CBA, so we need to write that CBA is 0 0 0, where A is LSB and C is MSB. Find the number of clock pulse at which the counter goes back again to this initial state. Mention the state of the counter for each pulse. So we need to find out the pulse at which the counter goes back again to 0 0 0, and we need to also write the transitions. So let's first write what are our inputs. So my J equal to K equal to J0, so let's just write J0, this one as 1 and this one as 2. J0 equal to K0 is equal to VCC, that means logic high, so it will be 1, and these are the negative edge triggered flip-flops. Then my J1 equal to K1 equal to, so this is connected to the output of this thing, so this is A, J1 is equal to A, J1 is equal to K1 is equal to A, and my J2 equal to K2 is equal to a dot b complement. Yeah, that is equal to a, this thing, a dot b complement, a dot b complement. So we can start with here clock 0, that is the initial case. So we have C, B, A as given in question, where C is the MSB and A is the LSB. So initially they were 0, 0, 0. At the first clock pulse, we have what we have. A will toggle to 1. B is simply equal to A, so A was 0 in previous cycle, it will remain as 0. C is equal to A dot B complement. A was 0, B complement is 1, so it will remain at 0. It will be 0, 0, 1. Now second clock pulse, my A is equal to 1, it will toggle. My B is equal to A and A is equal to 1, so it will toggle, it will be 1. And my J2 equal to K2 is equal to A dot B complement, so it is equal to A dot 1, so it will toggle, so it will be 1, 1, 0, right? Since A is equal to 1 and B complement is equal to 1, so that is J2 equal to K2 equal to 1, 1. That means my output C will toggle. Then the third one, it will be 1, and B is equal to, it will be B since it J equal to K equal to A, that is 0, so it will remain at 1. And this one here will be J2 equal to K2 is equal to A dot B complement, so A is equal to 0, it will remain at 0. J equal to J, since A equal to 0, that means J2 is equal to K2 is equal to 0, that means C will remain at 1, so it will be 1, 1, 1. Now my fourth one will be this will be 0. Now my output was 1, it will toggle, so it will be 0. And here my B is equal to 1, so it will, that means J2 is equal to K2 is equal to 0, so it will remain at 1, so it will be 1, 0, 0. Then my fifth cycle, so it will be 1. It was so it was 0, so it will remain at 0. And here my B is equal to 0 and my A is equal to 0, it will still remain at 1. Now my sixth clock cycle, it will be 0, it will toggle to 1. My B equal to 0 and my A equal to 1, so it will toggle, so it will be 0, 1, 0. Now my seventh clock cycle, so it will be 1, it will be 1 only, because my my J1 equal to K1 is equal to 0. And then this one, it will remain at 0, because J2 equal to K2 is equal to 0, so it will be 0, 1, 1. And finally the 8th clock pulse, it will be toggling. Since my A is equal to 1, so J1 equal to K1 is equal to 1, so this thing will toggle, so it will be 0. Since my A is equal to 1 and B complement is equal to 0, it will remain at 0, so since J2 equal to K2 equal to 0, 0. So after 8th clock pulse, at 8th clock pulse, my output will again be equal to 0, 0, 0. So the transitions that are made, so since we have two options here, so we need to write down the transitions also. So it will be 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, and 0, 1, 1. These are my states, and as you can see, option A is the correct answer and is following this sequence. So here we need to figure out what were the inputs. So J0 equal to K0 was 1, so it will always toggle 0, 1, 0, 1. J1 is equal to K1 is equal to A, so as you can see here 0 it will remain at memory state, here 1 it will toggle, 0 memory state, 1 toggle, 0 memory state, 1 toggle. And here C, that is output C, that is dependent on J2 equal to K2, that is A dot B complement. So A dot B complement, A dot B complement 0, A dot B complement 0, A dot B complement 1 toggling. So A dot B complement 0, no toggling, 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 A dot B complement 1 toggling, A dot B complement 0, no toggling, A dot B complement 0, no toggling. So and finally we got 0, 0, 0, and as a result these are the states that will be followed, and option A is our correct answer. This was question number 9. Now we can move forward to question number 10 of today's live session. So question number 10 states that for the circuit shown, which of the following sequence the counter state follows. So we need to look at this circuit and we need to find out the sequence that this circuit will follow. And let me just introduce my camera first. This was question number 10. Yeah. So question number 10 asks us, we need to find out the sequence that this circuit follow. So if we carefully examine this circuit, this is a D flip-flop connected with one another, and these are the positive edge trigger clocks. So here we know that D Q0 Qn plus 1 is equal to Dn for a D flip-flop. This thing we have to keep in mind. So here my D0 is equal to Q0 plus Q1 complement, that is a NOR gate. Since it's a NOR gate and its input connections are tapped at Q0 and Q1, so my D0 is equal to Q0 NOR with Q1, and then we have Q1 equal D1 equal to Q0, right? So if my Q0 and Q1, so Q1 and Q0 were 0 0, because all of the 4 options are starting from 0 0, so we will also assume that our initial states are 0 0. Then my D0, that is 0 NOR with 0, will be 1. So that means my Q0 will be 1 in next state, and D1 is equal to Q0. Q0 was 0, it will remain at 0. Then the next state is equal to Q0 NOR with Q1. So D0 will be equal to 1 NOR with 0, that is 0. So D0 Q0 will be 0, and Q1 will be equal to Q0. So that is D1 will be equal to Q0, that is 1. So that means 1 0. Then D0 is equal to Q0 NOR with Q1, that is again equal to 0. And Q0 D1 will be equal to Q0. Q0 was equal to 0, so that means D1 will be equal to 0. So we started with 0 0, then we moved to 0 1, then we moved to 1 0, and finally we moved back to 1 0, and so on. So the states are, number of states are 4, so mod 4 counter, and the state transitions are 0 0, 0 1, 1 0, and 0 0. 0 0, 0 1, 1 0, 0 0, then 0 1, because it will follow the same sequence. So option B is the right answer. After 0 0 it will have 0 1, after 0 1 it will have 1 0, then 0 0. So this is my correct answer, option B. So this was question number 10. Now let's just discuss question number 11. So the question number 11 asks, what is the modulus value of 5-bit Johnson counter? So modulus value is number of counting states that are possible in the counter. So for our Johnson counter, the structure is somewhat like this. We have this D flip-flop, we have Q, we have this Q complement. This D is connected to input of another flip-flop, D1, Q complement, D2, Q complement, and 4, D3, Q complement, and the output, the complement of the output of the last flip-flop is connected to the input of the first flip-flop, and this thing is also known as twisted ring counter. So the number of states for a twisted ring counter or Johnson counter are twice the number of flip-flops. So let's just say there are 4 flip-flops, then the number of counting states, the modulus of this counter will be 8 will be 8. So for a 5-bit Johnson counter, the number of flip-flops are 5. So my modulus of a Johnson counter will be equal to 2 into n, that is 2 into 5, and that thing is equal to 10. So 10 is my required answer. Now we can move forward to question number 12. So in this question we need to find out what is the mod value of the following asynchronous counter. So we are given this circuit and there are some tappings taken out, and that thing is applied to the reset of the flip-flops, and we need to find out what will be the modulus value of the following asynchronous counter. So we can draw here, we can draw here a clock. So this will be a clock, this is QA, this is QB, this is QC. So I am marking the falling edges, that is negative edges, because it's shown that is a negative edge triggered flip-flop. So here, 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 here. Now QA, for QA, J equal to K equal to 1. So when at the rising at the falling edges of the clock, my output will toggle. So let us assume it starts with 0 0 0, so it will toggle here only at the falling edges of the clock, it will toggle. Now I will mark the falling edges of QA. Why? QD is also there. Let me just mark it here. QD will be. So let's just read it C and this as D, because this thing is connected to the clock of the next flip-flop. That's why I am marking the negating edges of this. So the toggling will happen at the negative edges of the QA. Now I will mark the falling edges of QB, because that thing is connected to this flip-flop C. Let's just term it as C. So toggling will happen at the falling edges. So this is the falling edge of this, and QD will only toggle here. So this is 0 0 0 0, then it's 1 0 0 0, then it's 0 1 0 0, then it's 1 1 0 0, then it's 0 0 1 0, then it's 1 0 1 0, then it's 0 1 1 0, then it's 1 1 1 0, then it's 0 0 0 1, then it's 1 0 0 1, then it's 0 1 0 1 0. So let's just look at this thing, this NAND gate. This NAND gate is connected to the output of A first flip-flop, that is QA, and it's also connected to QD, and it's also connected to clock, that means the rising edge, falling edge clock. So this will be equal to 0, because we need to see when this will be equal to 0, because that thing will reset the whole counter. So this will be 0 when QA is equal to 0, when QD is equal to 0, and my clock is at falling edge. So, and this thing is equal to 0 when QA is equal to 1, QD is equal to 1. So this is NAND gate. This is a NAND gate. I thought it was an AND gate. This is an AND gate. QA is equal to 1, QD is equal to 1. and the clock is high. So that means as soon as QA and QD is equal to 1, so among the following cases, and clock is equal to high, so which means as soon as it reaches here, this point, reset will be there and these things will be paired and it will again start at 0 0 0. So this thing will count from 0 0 0 to 1 0 0 1, that is from 0 to 9, that are 10 states. So this is a decade counter or mod 10 counter, because the moment the clock rises, this at QA equal to QD equal to 1, this thing will be reset and it won't count 1 0 1 0. 10th, that is 1 0 1 0, that is the 11th state, and the 10 number will not be counted because it will reset immediately. So it will only count from 0 to 9, that are 9 states, and it is a mod 10 counter. So next question is, what are the minimum number of flip-flops required to design a mod 150 counter? So we need to find out the number of flip-flops required to design a mod 150 counter. So we know that modulus of a n is equal to mod n is equal to n is simply equal to mod n. So n, the modulus of a counter, is equal to 2 raised to power n, where n is the number of flip-flops. So here n is equal to 150, so 150 is equal to 2 raised to power n. So let us assume n is equal to 7, that means 2 raised to power 7 is equal to 128. So this thing should be equal to n, should be 2 raised to power n should be equal to, this now is an equality, here should be 2 raised to power n should be greater or equal to this thing, greater or equal to this thing, because it won't be in modulus, won't be in this power. So that's why we have this inequality here. So 2 raised to power n should be greater or equal to this. So for n equal to 7, that means 150 is less or equal to 127. That's not true. So that means n equal to 8. So 2 raised to power 8 is equal to 256. That is greater or equal to, that satisfies this condition. So that means the minimum number of flip-flops required to implement mod 150 counter is 8. So what was the condition? 2 raised to power n should be greater or equal to n, where n is the mod and small n is the number of flip-flops. So while having this condition, we put the n equal to 8 and we found that minimum value of n to achieve this thing is 8. You can see that n equal to 9 can also satisfy this condition, but we need to find out the minimum number of flip-flops that can satisfy this condition. Now question number 14, it says that the number of flip-flops required for the synthesis of a sequential logic circuit with 12 states is. So we need to find out the number of flip-flops required for the synthesis of a sequential logic circuit with 12 states. So this thing is equal to, we know that earlier we found out this mod n is equal to 2 less or equal to 2 to the power n. Let's just assume an equality here, n equal to 2 to the power n. So that implies n is equal to log 2n. We use a ceiling function here and we write the number of flip-flops required to implement this thing is equal to ceiling function of log 2n. This ceiling function of log 2n. So we can get this answer from this also. So I can write n should be less or equal to 2 raised to power n, and from that I can say that n is equal to 4 simply, because if I put n equal to 3, that means 2 raised to power 8. So 8 is less than 8 is greater than 12. That's violating the condition. So 2 raised to power n equal to 4 equal to 16, greater or equal to 12. So that thing is true. So n equal to 4. I can directly write that. But we can always have this thing and this thing that I told here. 2 raised to power n should be greater or equal to n is written in this form as n is equal to ceiling of log 2 of n. So you know the ceiling function, it gives us the least integer greater than the number. So if the number was my 3.1, so the ceiling of 3.1 is 4. If my number was 4.2, we need to find out the least integer greater than the number itself. So 5.1 has a ceiling function equal to 6, 6.5 has a ceiling function equal to 7. So that thing, so n is equal to ceiling of log 2n. So log 2 of 12 is log 2 of 12 is, if you can use your calculators and find, it's 3.58, and ceiling of 3.58 is 4, so n is equal to 4. This thing compressed in this thing is simply this thing, so n is equal to 4. Let's just take a 2-minute break here. So as you can see, there is no one in this live session. To those who are watching the recording, they can seek or move forward by 2 to 3 minutes and have a look at question number 15. So now let's just discuss question number 15 of today's live session. So the question 15 states that a 4-bit counter is designed using JK flip-flops. What will be the value of counter after giving 18 clock pulses, assuming that the value of the counter before giving any clock pulse is 1? So here we have a 4-bit counter which are made up of a JK flip-flops, and the first state before giving any clock pulse is 1, and we need to find out what will be the state after I apply my 18th clock pulse. So the transitions are going simply from 1 to 3 4 5 6 7 8, and we need to find out what will be my state after I apply 18th clock pulse. So initially I am at 1, and also when I talk about 4-bit counter, so that means it will count 2 raised to power 4, that is 16 states from 0 to 15, and once it will hit this 15, it will go back to 0. So as given in the question, I am starting at state 1, then I am making a transition to 2 after first clock pulse. So this will implies after first clock pulse, similarly after second clock pulse, and so on. I have to write all because I need to count the number of clock pulses at the end. So 9, 10, 11, 12, 13, 14, 15. So now I'm at 15th. So after 15, what will be my state? It won't be 1, it will be 0. So condition on this counter was, it was initially at 1, not at 0. But once I am at 15th state, I won't go back to first. I won't go back to number 1. I'll go back to 0 state. That is 0 0 0. So it will be 0 0 0. Then it will be 1. So how many clock pulses are there? 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16. So this is 17. At 17th I will be at 2nd, and after 18th I will be at 3rd. So after 13th clock pulse, 18th clock pulse, I will be at state 3. So the value of counter, not state. State will be different. State is different thing. So the value of counter after 18th clock pulse will be 3. This thing if it was 0, it would have been at 4th. That's the only difference. So it will have been 0, 1, 2, 3, 4. So it will be 2. That's why 2 is given here to create a confusion. So it will be 0, 1, 2, 3, 4, 5, 6. It will be 15, 0, 1, 2. That's why option 2 is given here. So in case there is a confusion, people might mark 2 as their right answer. But the correct answer to this question is 3, because we are starting from state 1 as given in the question. value of the counter was 1. Now question number 16, which of the following statements is not true? The internal 2 input AND gates are useful in counter ICs to effect asynchronous reset to obtain different modulo numbers. This thing is true, you know this. Option C, let us first read option D. A circuit for digital clock can be made using counters. We saw it, how it can be made. It's correct. Option C, IC7490A provides a fixed asynchronous preset of 1001 along with asynchronous reset module numbers. This is also correct. You can refer to your lecture notes if you want to understand it better. And option B, using asynchronous counter, counting state 0 cannot be enforced early. This is a wrong statement. This is a false statement. So the statement which is not true is option B. For more on this, you can refer to your lecture notes. Now, question number 17. It states that the maximum clock frequency in megahertz of a 4-stage ripple counter. So the maximum clock frequency of in megahertz, we need to write the maximum clock frequency in megahertz of a 4-stage ripple counter utilizing flip-flops with each flop having a propagation delay of 29 seconds. We saw it question earlier. Actually in live sessions I used to give students questions to solve, then I used to show them the solutions. As the participants are decreasing and the number of participants are decreasing, and right now there is no participant, so I'll just show the solution. But I request you guys to try to do these questions, whoever is watching the recordings and all, try to do these questions first, then refer to the solutions. With that way, that will be better. You can see where you are going wrong, and maybe you are solving it in different method. That's a lengthy method, and this one is a better method, that to understand. So try to pause the video, try to solve it, then refer to the solutions. Whether you solve it correctly, but still refer to the solution, because sometimes there is another method that's way more easier and way more helpful in terms of the exams. We always try to find out the methods that are quite easy to understand and quite easy to do. So stop your clock, stop the video and pause the video and do the question. For all, I just forgot to mention it, and maybe next time I can give the instruction at the start, so that will be helpful. So what is given in this question is a 4-stage, so it's a 4-stage ripple counter. So n is equal to 4. So what is a ripple counter? So we can have a ripple counter. We have this T flip flop, this is 1. We have this Q, this is clock. It can be positive or negative edge triggered. Let's just assume it's a positive edge triggered. Then this output is connected to the clock of this thing, so this is T equal to 1. Then this is connected to this thing, T equal to 1, and then this is connected to this thing, T equal to 1, and this equal to 1. This is a ripple counter, and each stage is having each flip-flop is having a delay of 20 nanoseconds. So the overall delay will be equal to n multiplied by the individual propagation delay, and the frequency, the maximum allowable frequency will be f clock will be equal to 1 by n into TPD. So it will be 1 by 4 into 20. It will be 1 by 80. It will be 1 by 8. It will be 30. It will be 1 by 8. So it will be 0.31. It will be It will be 0.125 into 10. It will be 1 point. So 1 by 80 is how much? 1 by 80. It will be 0.125 into, so 1 by 80. You just write 1 by 80. So 1 by 80 is 0.0125. Let me just check it. 1 by 80, 0.0125. But we have to write answer in megahertz. This thing is in gigahertz. Why? Because I have written 20 directly here. this is 20 nanoseconds. So 0.0125 multiplied by 10 to the power 3 will give me answer in megahertz. So that is 1, 2, 3, that is 12.5 megahertz. So this thing is 12.5 megahertz. Always keep note of these units. Whatever units you are using, keep note of it. Try to use everything in SI, but since the question was demanding in megahertz, so that's why I converted it into megahertz. Now to the last question of today's live lecture. So the digital circuit shown is, so we need to find out what is this digital circuit shown below, right? So here, as you can see, let me just mark it 0, 1, 2. D0 is equal to Q2 plus Q1 complement, and D1 is equal to Q0 and D2 is equal to Q1. So let's just assume we start at 0, 0, 0. This is Q2, Q1 and Q0. My next state will be equal to Q2 NOR with Q1, this will be 1, and Q0 equal to D1, so it will be 0, and this will also be 0. Then next state will be 0, this will be 1, this will be 0. Then next state will be again, so let me just check, yeah, 0, 0, 0, 0, 0, 1. So Q0 is equal to Q2 plus Q1 complement. Q2, okay, this is also 1, Q2 plus Q1, I thought it's Q1 plus Q0. It will be 0, 1, 1. Then it's Q0, then it's Q2 plus Q1, so 0 plus 1 is 0, 1, its complement is 0, so it will be 0, it will be 1, it will be 1, then it will again be equal to 0, this will be 0, this will be 1. Why I'm writing it this quickly, so what I'm doing is, for Q0 I'm taking a look at Q0, Q2 NOR with Q1, so 0 NOR with 0 is 1, and D and Q2 and Q1 I'm writing simply like this, like this. Now I have to take NOR of this. 1 NOR with 0 is 0, and this will come here, this will come here. So I'm again back to 0, 0, 0. So how many states are there? 1, 2, 3, 4, 5. Not this one because it's the previous state only. So there are 6 states. So it's a divide by 5 counter, and the states are 0, 1, 3, 0, 1, 3, 6, 4, and again to 0. So the transitions are 0 to 1, 1 to 3, 3 to 6, 6 to 4, and 4 to 0. So that was all for today's lecture. Thank you to those guys that are watching the live recording, that are watching the recording. They can. That's all for today's lecture. Maybe since there's some time left, I can wait up to 4:30 p.m. Maybe someone won't join, then I can close the session. So thank you. So next week we'll meet at same time, that is from 3 p.m. to 5 p.m. So the lecture will be on 9th April, Sunday, and we will discuss questions related to, I think, sequential circuits. Yeah, questions related to design of synchronous sequential circuit using Mealy and Moore model, state transition diagrams, algorithm state machines, ASM chart, state reduction technique. So next week we will be discussing week 10. So now we are left with only 3 live sessions, 10, 11, 12, and 11th and we are going to discuss DACs and ADCs, and 12th we are going to discuss memory organization. So 3 live lectures are left. I request you all to attend the live sessions. If not possible, do refer the recordings. Whatever will be feasible to you, do it. So that was all for today's live lecture. Thank you. So I'll just wait for 2-3 minutes. Maybe some people might join in case. If not, then I can end the session. I think I can end today's live session. So thank you all for joining. We'll meet next Sunday from 3 p.m. to 5 p.m. discussing week 10 problems. Thank you.